Convolutional neural networks. So there's a problem with multi-layer artificial neural networks. They don't learn structure in the inputs. So the predictions do not depend on the order that the inputs are listed in. But it's a key concept that we need to learn structure. Most data sets have structure. Word order matters in a sentence. How now brown cow? How brown cow now? Cow now brown. How? And there are relationships between a given pixel in an image and those pixels that are around it. Here's a picture of a puppy, and here's the same picture. It's all the same pixels, just in a different order. So data is often from a complex process with an underlying topology. So how do we model topologies? For example, the order of the inputs. Well, it's a major motivation for our machine learning libraries, like TensorFlow. A tensor has multiple indices. A vector has one index, a matrix two, images tend to have three indices, batches tend to have four indices, video five, and you can go on and on. The TensorFlow logo implies tensors. Notice that they look different from different viewpoints, from different view planes. And we'll be using PyTorch, which also features tensors, because they allow high variety in the data structures used. We often will convert tensors to and from multi-index NumPy arrays, so implementation's not a big deal. They're often like using NumPy. But we'll get certain sublibraries that are specific to certain structures of the data, for like Torch Audio, Torch Geo, and Torch Vision. Convolution, for example, is used to study time series in images. And images tend to be studied using Torch Vision. So convolution is related to linear algebra. It's a type of linear transformation. It applies a fixed kernel from a space K to vectors in V via an algebraic operation known as convolution, denoted by the asterisk. Foundational in signal processing, we can use signal processing, in fact, to motivate convolution by using a kernel on a signal to obtain a moving average. So here's my signal, here's my kernel, and I'm going to get my result is going to be a moving average. So I take the 1/2 times 0 plus 1/2 times 2, and I get 1. Then I move my kernel, 1/2 times 2 plus 1/2 times 4, and I get 3. And then I just slide my kernel across my signal, and what I end up with is a moving average. This is a convolution. Here it is with a different kernel, but once again, we apply the kernel, get 1.5, we slide the kernel then across the signal, and get a different weighted moving average. So convolution is also an algebraic operation. If I've got a vector space V whose structure is an R regular graph or network, G equals V vertices and E edges, and by R regular I mean all the vertices have exactly R neighbors, then F in V means that there is a coefficient for F for every vertex in V, and it's a real coefficient. If G is a path, then F is a signal. That is, if we have this path, V1 to V2 to V3 and so on, then we get a corresponding signal as our vector. For each V in our vertex set, we define a bold italic F sub V, which is a vector in R plus 1, and it's the set of coefficients corresponding to V and the vertices in its neighborhood. For example, here I have a bunch of vertices and their relationships. So if I take the V2 here, it has neighbors V1 and V3. That means my F sub V2 is this vector. And you can see I can just slide along looking at who the neighbors are. Here's F sub V6, and that's corresponding to the V6 and its neighbors, and so on and so forth. At the ends, we can either pad with zeros or omit or start over or replicate, whatever we need to do. So here on the far left, we don't have a neighbor on the far left, so we just pad with a 0. Now, if I have H and R sub R plus 1 or super R plus 1 and F is in V, I can define the convolution of F with H as F convolution H is the vector of inner products of F sub V's with H's. And with padding, that would also be another vector in vector space V. For V equals Rm and R here less than M plus 1, F convolution H is a vector of inner products of F with all shifts of H padded by zeros. Let's take a look. Here's my F, here's my H. So what I do is I pad with zeros, and I get this value, which is 1. And then I shift and pad with zeros. And then I shift and pad with zeros. And I continue doing that, 1, 3, 5. And so my convolution is actually 1, 3, 5, 7, 9, 11. Notice that I didn't use padding here, so I actually ended up with F star H, F convolution H, is in a smaller space. So convolution is not just an algebraic operation, it's a linear algebra operation. So if I define T of X as X star H, X convolution H, then it's a linear transformation known as a convolution transform with convolution kernel H. Often, the vector space W is the same as V, and depending on how we handle padding and stride, how much we shift each time. We may not have W equal to V, but we can use padding and manipulate the output so that we get the same shape if we need that. Convolution transforms commute with each other when they have the same initial and final spaces. So not every linear transform is a convolution. That is, we're not replacing the concept of matrix transforms where you do not have commutativity, but we're augmenting them. So let's go to convolution of an image. Here I have my convolution kernel, and as an image, this set of ones and zeros is actually the word high. You can see the structure if I do a little bit of shading. So my convolution kernel is all negative ones with an 8 in the middle. Notice if I add all that up, I get 0. That's actually significant. So if I apply it here, then I get 0, and I put a 0 in the corresponding part over there. If I apply it here, I get a 5, and I put a 5 in the corresponding place over there. Here I'm going to get zeros, and I insert a 0. And this is what the entire result looks like. This is the convolution. As an image, it looks like this. Now there are two concepts at work here. The convolution is a mathematical operation, lots of algebraic structure and properties, requires properties beyond the image, zero padding sometimes. But where do we get the coefficients for the kernels? Well, that's 300 years of applied math. And intuition can play a major role. Sometimes. Now this is actually an important kernel. It's an edge detector, something that people discovered can locate edges in an image. But for us, convolution kernel coefficients can be learned. Convolution often is a layer in a deep neural network. So where we have the image comes in and convolution is applied to it, and then it goes out and gives us this result. And then we back propagate to figure out how to change these coefficients so that we get better convolutions for whatever our purpose is. And typically a convolution layer learns many convolutions, and they are called feature maps. Now there's also a concept of subsampling and pooling. See, our goal here is machine learning, and so we often reduce the size of the image using blocks. So here we make it into sub-blocks of 2 by 2. Max pooling, it's just the max value in each block, as you can see here. Subsampling is weighted averages, and subsampling is actually learnable. So max pool or subsampling, well, it depends on your application. So the results of convolution are feature maps, And you can put all of these convolutional layers together, and you can end up with a convolutional neural network. Many different layers with many different convolutions and subsamplings or max pooling. An artificial neural network, MLP for example, is the final classifier at the very end. So the convolutions are representational learning followed by our UFA, which is an A and N. So what about as classifiers? Well, here's the process. You build complex images out of smaller, simpler sub-images. So here's our first layer representations and second layer and third layer. And the convolutional neural networks learns how to construct images from one scale to the next. So here you can see how it would use these layers to construct faces, and then cars, and then elephants, and then chairs. But the small pieces at the bottom are actually common to the entire data set. This is sort of its primitive structure, its primitive alphabet that it can use to build all these other images. And we often use dropout to control overfitting. Training is in steps, backpropagation steps, stochastic gradient descent steps. So if the dropout rate is 10% for some layer, then only 90% of its weights are trained in each step. And we typically select that 10% uniformly randomly. And that reduces overfitting because not all the neurons see the data in each training step. Here's the UNet standard for all of this. So a feature mapper is a convolution block with a convolutional layer, a batch normalization. It's essentially a learnable standard scaling, so where it learns the gamma and the beta. A ReLU activation, and then max pooling. So here's convolution for images. We saw that earlier. Here we are now going to apply the ReLU, and all these negatives are going to go to zeros. And notice I shaded where I have zeros is actually what's shaded in black. So it's black. Everywhere you see the dark color, it's zero after the ReLU. And then I do a max pooling, and you can see what's happened. When I look at this as an image, I've isolated the H. I'll need different kernels to isolate the I, but you can see how this feature mapper approach can pull these images apart and learn the different parts of the images. So let's look at the MNIST digits example. This is for PyTorch, but it would be similar if you were using TensorFlow. Each is a 28 by 28 pixel image. There are 70,000 training, 10,000 testing. So we have our image, and it goes through this first block, and then it goes through this second block, and then it goes through our fully connected final layer, our artificial neural network. That means we have two feature mappers followed by our artificial neural network. So here's the PyTorch code for a UNet feature mapper. But notice all these numbers. How do we know which numbers to use here? Well, our images are grayscale, so there's one color channel. It would have been 3 if these were red, green, blue. This is the number of new features that we're going to create. Remember, this is representation learning, feature engineering. These are called output channels. 5 by 5 kernels. Well, it depends on the image size and the object sizes within the images. So this is really something you have to experiment to figure out what's best. And the stride is the distance to slide each step. And 5 by 5 kernels overlap 2 padded pixels at the image boundary, as you can see here. So we do a padding of 2. So notice that the 16 and the 16 are the same here. That's the out from the first to the input to the batch norm. They have to be the same. But why 16? How do you choose the number of out channels? Well, implementation, you probably should use a power of 2. It's a lot easier to implement if you're using GPUs. And you probably want to use large early and smaller late. So our goal here is highly complex models which may overfit, but then can be controlled by the smaller layers later. So let's also mention that you should look at similar models that work. People have done massive amounts of experimentation. Take advantage of their experimentation. So in summary, convolution is a signal processing operation for filtering data, for detecting features in the data, and convolutional neural networks combine 300 years of applied math with convex loss function driven neural networks. And they're a major motivation for the deep learning libraries, Theano, TensorFlow, PyTorch, and many others.